In the summer of 1942, a housewife in Ohio walked to her local collection center carrying a frying pan, a coffee percolator, and a garden hose fitting. She handed them over without hesitation. Within months, that metal would be part of a bomber flying over Europe. Aluminum is everywhere today. It forms the skin of commercial aircraft, the frames of skyscrapers, and the packaging of consumer goods. But less than a century ago, this metal was rare, expensive, and difficult to produce. Its transformation from a laboratory curiosity into the backbone of modern industry required decades of engineering innovation, corporate expansion, and a global conflict that turned scrap metal into national strategy. In the early 19th century, aluminum existed only as a chemical curiosity. Scientists knew the element was abundant in the Earth's crust, locked inside compounds like bauxite ore, but no one had developed a practical method to extract it in pure form. The few samples that existed were produced through labor-intensive chemical processes that made aluminum more expensive than gold. The challenge was not scarcity of raw material. The problem was energy. Separating aluminum from oxygen required breaking incredibly strong molecular bonds. Traditional smelting techniques which worked for iron and copper proved ineffective. For decades, aluminum remained a metal without a market. The solution arrived in 1886, independently discovered by two young chemists working on opposite sides of the Atlantic. Charles Martin Hall, a recent college graduate in Ohio, and Paul Héroult, a French metallurgist, both developed the same electrolytic process within months of each other. Their method used electrical current to dissolve aluminum oxide in molten cryolite, allowing pure aluminum to separate and collect at the bottom of the smelting pot. The Hall-Héroult process transformed aluminum from a laboratory oddity into an industrial commodity. For the first time, manufacturers could produce the metal in commercially viable quantities. The price dropped from $12 per pound in 1880 to less than $1 by 1890. What had once been a precious metal used for jewelry and novelty items could now enter industrial production. But the process came with a steep requirement: electricity. Aluminum smelting consumed enormous amounts of electrical power. A single ton of aluminum required approximately 15,000 kilowatt-hours of energy. This demand would shape the geography of the aluminum industry for the next century, concentrating production facilities near hydroelectric dams and other sources of cheap, abundant power. In 1888, Charles Martin Hall partnered with a group of Pittsburgh investors to establish the Pittsburgh Reduction Company, which later became the Aluminum Company of America, known as Alcoa. The company secured exclusive rights to the Hall-Héroult process in the United States and began constructing smelting facilities near sources of hydroelectric power. By the early 1900s, Alcoa had established a near monopoly on American aluminum production. The company controlled bauxite mines, refining facilities, and smelting operations. It invested heavily in research and development, improving the efficiency of the electrolytic process and reducing production costs year by year. Alcoa's dominance extended beyond manufacturing. The company worked to create demand for its product by developing new applications and partnering with manufacturers in emerging industries. Aluminum found early uses in cookware, where its lightweight and heat conductivity offered advantages over cast iron. It appeared in electrical transmission lines, where its conductivity and low density made it more practical than copper for long-distance power distribution. But the most transformative application would come from an industry that barely existed when the Hall-Héroult process was invented: aviation. The Wright brothers' first powered aircraft in 1903 used a custom-built aluminum engine block to save weight. The choice was deliberate. Aluminum offered a strength-to-weight ratio that no other readily available metal could match. As aviation technology advanced through the 1910s and 1920s, aluminum became increasingly central to aircraft design. Early aircraft used wood and fabric for their structures, but these materials had limitations. Wood could warp, split, or rot. Fabric deteriorated under exposure to weather and stress. Engineers recognized that metal construction offered durability and strength, but steel was too heavy. Aluminum, particularly when alloyed with small amounts of copper, manganese, or magnesium, provided the solution. The development of duralumin in Germany before World War I marked a critical advancement. This aluminum alloy combined lightweight with tensile strength approaching that of steel. By the 1920s, aircraft manufacturers in Europe and America were designing all-metal aircraft with aluminum fuselages, wings, and control surfaces. Boeing, Douglas, and other American manufacturers adopted aluminum construction throughout the 1930s. The Boeing 247, introduced in 1933, was an all-metal passenger aircraft that established new standards for speed and reliability. The Douglas DC-3, which entered service in 1936, became the most successful commercial aircraft of its era, with aluminum construction enabling its durability and payload capacity. As aircraft became larger and more complex, aluminum consumption in aviation grew exponentially. A single DC-3 required approximately 2,000 pounds of aluminum. Military bombers being developed in the late 1930s would require far more. By 1939, the United States produced approximately 300 million pounds of aluminum annually. Alcoa remained the dominant producer, but demand was rising across multiple sectors. The automotive industry used aluminum for engine components. The construction industry incorporated it into window frames and architectural elements. The electrical industry relied on it for power transmission. Then came the outbreak of war in Europe. Britain and France, facing Nazi Germany's expanding air force, placed urgent orders for American-built aircraft. These orders created immediate pressure on aluminum supplies. Aircraft production, which had been modest throughout the 1930s, began accelerating rapidly. The United States government recognized the strategic importance of aluminum and began pushing for expansion of production capacity. New smelting facilities required years to plan and construct. Existing plants could increase output, but only to a limited degree. The industry faced constraints in electrical power supply, bauxite mining, and refining capacity. By 1940, with war spreading across Europe and American defense spending increasing, aluminum had become a material of national security concern. When the United States entered World War II in December 1941, the demand for aluminum became acute. The military aircraft planned for production required aluminum in unprecedented quantities. A B-17 Flying Fortress bomber used approximately 30,000 pounds of aluminum. A B-24 Liberator required even more. Fighter aircraft like the P-51 Mustang, though smaller, still consumed several thousand pounds each. American war planners projected the need for tens of thousands of aircraft over the coming years. Meeting this demand would require more than doubling national aluminum production. The government invested heavily in new smelting facilities, particularly in the Pacific Northwest, where hydroelectric dams provided abundant power. The Defense Plant Corporation financed construction of new plants that increased American aluminum capacity from 600 million pounds in 1941 to more than 2 billion pounds by 1943. But increasing production capacity took time. Smelting plants required 18 to 24 months to design, construct, and bring online. In the meantime, a gap existed between demand and supply. The solution came from an unexpected source: household scrap metal. In the summer of 1941, before the United States entered the war, local communities began organizing metal collection drives. These efforts intensified dramatically after Pearl Harbor. The War Production Board, established to coordinate industrial mobilization, launched nationwide campaigns encouraging civilians to donate scrap metal for war production. Aluminum became a particular focus. Newspapers, radio programs, and newsreels explained that old pots, pans, coffee makers, garden tools, and other aluminum household items could be recycled into aircraft components. Collection centers appeared in towns and cities across the country. Civic organizations, schools, and local governments organized drives. The response was substantial. Families brought cookware, lawn furniture, and decorative items. Some communities collected tens of thousands of pounds in single-day events. The donations served both practical and symbolic purposes. Practically, recycled aluminum could supplement industrial production, though the total quantity remained small compared to primary production from bauxite ore. Symbolically, the scrap drives connected civilian life to the war effort, giving families a tangible way to contribute. Recycling aluminum presented technical challenges. Household items were made from various aluminum alloys, often contaminated with food residue, paint, or other materials. Industrial recyclers developed methods to sort, clean, and remelt scrap aluminum, separating it by alloy type and removing impurities. The recycled metal could then be incorporated into new production runs. By the end of the war, Americans had donated hundreds of millions of pounds of aluminum scrap. The actual military value of these donations remained difficult to quantify. Some historians argue the scrap drives provided more benefit through boosting civilian morale than through material contribution to aircraft production. Others note that every pound of recycled aluminum freed up industrial capacity for primary production from bauxite. Regardless of its exact material impact, the aluminum scrap drive became one of the most visible symbols of home front participation in the war effort. Between 1941 and 1945, American industry produced nearly 300,000 military aircraft. This output required approximately 6 billion pounds of aluminum. The expansion of production capacity, combined with improvements in recycling and process efficiency, enabled manufacturers to meet demand. Aluminum production became a strategic priority comparable to steel, oil, and rubber. The government controlled allocation of aluminum supplies, directing material to aircraft manufacturers, shipbuilders, and other essential military production. Civilian uses were severely restricted. Aluminum cookware disappeared from retail stores. Building construction using aluminum ceased for the duration of the war. The industry employed hundreds of thousands of workers in mining, refining, smelting, and fabrication. Women entered the workforce in large numbers, taking positions in smelting plants and aircraft factories. The pace of production was relentless, with facilities operating around the clock to meet military contracts. By 1943, the United States had become the world's largest aluminum producer, a position it would maintain for decades. When the war ended in 1945, the aluminum industry faced a sudden collapse in military demand. Aircraft production dropped precipitously. Smelting facilities built for wartime production now had excess capacity. The industry needed to find new markets. The solution came through aggressive expansion into civilian applications. Alcoa and other producers invested in research and marketing, promoting aluminum for construction, transportation, and consumer goods. The post-war housing boom created demand for aluminum siding, window frames, and roofing materials. The automotive industry increased its use of aluminum for engine blocks and transmission casings. Perhaps most significantly, aluminum found widespread use in packaging. The development of the aluminum beverage can in the 1950s created an enormous new market. By the 1960s, aluminum cans were becoming standard for soft drinks and beer, eventually replacing steel cans in most applications. Commercial aviation expanded rapidly in the post-war decades, driving continued demand for aluminum. Jet airliners, introduced in the 1950s, required even more aluminum than their propeller-driven predecessors. The Boeing 707, Douglas DC-8, and other first-generation jets established aluminum as the fundamental material of aircraft construction. Global production of aluminum grew from approximately 2 billion pounds in 1945 to more than 30 billion pounds by 1980. New producers emerged in Canada, Europe, and other regions with access to cheap electrical power. The industry became truly international, with bauxite mined in tropical regions, refined into alumina in intermediate facilities, and smelted into pure aluminum near sources of hydroelectric power. Today, aluminum ranks as the second most widely used metal in the world, surpassed only by iron. Annual global production exceeds 100 billion pounds. The metal appears in structures, vehicles, packaging, electronics, and thousands of other applications. The aerospace industry remains one of the largest consumers of aluminum. Modern commercial aircraft like the Boeing 777 contain approximately 100,000 pounds of aluminum alloys. Military aircraft continue to rely on advanced aluminum alloys developed through decades of research. The recycling of aluminum has become an established industry in its own right. Unlike the emergency scrap drives of World War II, modern aluminum recycling operates as a continuous industrial process. Approximately 75% of all aluminum ever produced remains in use today, recycled and reformed repeatedly. Recycling aluminum requires only 5% of the energy needed for primary production from bauxite ore, making it economically and environmentally efficient. The transformation of aluminum from a rare metal to a fundamental material of modern civilization required contributions from scientists, engineers, industrialists, government planners, and ordinary citizens who once brought their cookware to collection centers. The metal that enabled aviation, packaged consumer goods, and changed the possibilities of architecture began its journey to ubiquity in laboratories and smelting facilities where the challenge of extracting it from ore was finally solved. The story of aluminum encompasses more than wartime sacrifice. It represents a century of industrial development, from the discovery of an efficient production process through the creation of a global industry. World War II accelerated aluminum production and demonstrated its strategic importance, but the metal's significance extends far beyond that 4-year period. The investments made during the war, the production capacity built, and the recycling infrastructure developed all contributed to aluminum's post-war expansion into nearly every sector of modern life. What began as a solution to the problem of extracting a lightweight metal from common ore became the foundation of industries that define the contemporary world. For the next video, you can watch what happened when America had no ball bearings in 1940.